Let's look at Euler's method. This method is a numerical method for ordinary differential equations. Let's try to make it as simple as possible. Suppose we solve a single equation. This single equation involves the function y whose derivative is twice the function y. So that's the governing equation. And this y, at least we know a point of the curve. So we try to determine if we can find such a curve, y as a function of t. So that is, if we show this is t and y, we're trying to determine a curve satisfying the equation. So let's just symbolically just try to imagine whatever curve. And if this curve, when t is 0, it is 1, that means it has to pass through this point, right? 0, 1. So we want to find a curve that will pass through this point. Yeah, so it can be defined for all real values of the t. But so this is a solution curve we're looking for. We only know one point of the curve, but how can we find an approximation to the curve? So that's the question. And if we write a more general case, you see this equation can be written in a general case that is an equation, a differential equation of y. Okay, so this is the derivative on one side, and the one expression that is depending on y or t, right, and or t on the other side. So this f means some expression of t and y. So that means a general case can be time dependent on the right hand side. Also, it can depend on y. So you have this governing equation and the initial data. So at a certain t, the y value is given. So just as the example shows, at a certain t, for example, when t is 0, the y value is 1, right? So the y value is given at a certain t value. So we call this problem an initial value problem. So to solve this initial value problem using Euler's method, so we want to find approximate solution at a number of values of t. So first, in the direction of t, we want to discretize. That is, I start with the t0, right? In this, it doesn't have to be 0. So t0 can be 0 or can be another value. So it is a point when t is t0, what is y? Y is 0. The y value is given. So that is the point that the curve will go through, will pass through. And then I also want to know at t1 the y value, at t2 the y value. So t1, t2, then they're equally spaced. So we assume the step size is h. So increase by h. So that means the t1 is T0 plus H, right? That's one step away from T0. And T2, you have to add another step to T1, so which is 2 steps away from T0. So then each step you do, you get another point, T3. So they're equally spaced. So this way we hope to be able to find a number of y values for each Ti. So this the sequence of T values. So we hope to find the y value, approximate y value. So then that will be our approximate solution curve. So H is called step size. Certainly when J is 1, that's the step 1, that you get T1. When J is 2, you get T2. So etc. And we can look at the numerical integration of the differential equation and the graphical interpretation. When you see the bold face curve, that represents an exact solution to an ODE. So that solution curve is the exact solution, this bold-faced one. And this solution curve is not known except one point, right? So we only know the initial data. At T0, we know the y value, y0. So that's the only point of this curve that we know. So how can we get approximation to the curve? So that is our task. But don't forget, we have the governing equation. The governing equation tells us actually information about the curve. So we need to look at the governing equation. So if we have such an equation with the right-hand side being some expression of Ty, so this expression is given because your problem is a specific problem, then this expression on the right-hand side is a very specific expression, right? Such as 2y, right? So it can be, it is just a concrete expression. So this, that means at the very beginning point, if I put that initial point T0, Y0, then I know the slope at that point because that is the governing equation, right? When that's the derivative at the first point, T0, Y0. So we can immediately know at this point the slope of the curve. So you know that means the tangent line slope can be found. So this tangent line to the curve, its slope can be determined using that right-hand side function, evaluation at T0, Y0. So once you know the slope, you also know a point, then immediately you can determine the tangent line. So it's actually a tangent line approximation to the curve at this very specific point, right? So you just draw a tangent line. So we can quickly write passing through the point, the slope is this quantity and the t minus t0. So we have the tangent line equation because we have, right, 1 point. The 1 point and the slope, then slope point form gives the equation. So this equation is the tangent line approximation to the solution curve. And we can write it as y0 plus the slope. But if you think the t, suppose I choose t1, let's see how can I, because this t0, t1 are close to each other when the step size is small. So, and at t1, we can use the tangent line to approximate. So let's just simply consider the next point. At t1, what is the y1? So I'm going to get y1 and t1 minus t0. Remember, t1 minus t0, it is h, right? The one that is the distance between t0, t1. So we put h, and h times the slope of the straight line f t0, y0. So this y1 can be found. So we suppose this, you draw the tangent line, you go all the way here, and then that is simply the tangent line evaluated at t1. So that is our y1. Y1 is just the approximate y value of the solution. So look at this exact solution. Actually, the true value is here, right? If I put a little dot, that is at t1. However, our y1, you see, differ from the true solution by how much? Then you can see the vertical distance. So that's highlighted in this color. So you can see that's the error. So, okay, but we have already applied one step of Euler's algorithm to calculate the next node. So if we continue this pattern, then we can generate y2 using y1. So the formula will be y2, y1 plus h, and this direction field evaluate at t1, y1. So then we can calculate the y2. So this way we get y2 from the previous value t1, y1. We can find y2. So continue this pattern, we get a formula which is called Euler's method. So it's actually y plus 1 is the previous y value plus h, slope function, ti, yi. So when I is 1, we get y1. Actually, when I is 0, right? From y naught, we can get y1. When I is 1, from y1, t1, we can get y2, etc. So can continue. The notations. So you see we here the function, that's the exact solution, which was plotted as a boldface curve. And this is the evaluation of the exact solution at Tj. But the approximate solution is denoted by y sub j. For example, y1, y2, yj, etc. So that is the approximate solution at a certain Tj. So when you use approximate solution y and Tj, yj, because yj is approximate solution at Tj, and then you get approximate slope at Tj. So that is only approximate slope function, right? Which is the right-hand side function. And so Euler's method can be viewed as a Taylor series expansion after we truncate the higher power terms. So let's consider the Taylor series expansion at the neighborhood of T0. So T0, and this is the solution curve, and we expand the curve at the point T0, and then remember we can use the y at T0, the derivative of y at T0, and second of derivative of y at T0, and then get this Taylor series form. But for this Taylor series, we truncate all these from the second degree. Yeah, we truncate all these terms and keep only this portion. So certainly the right-hand side is not the same as the curve, the solution curve. So it is just a linear approximation to the solution curve at the neighborhood of T0. So this linearization of the solution curve. Then what is this y derivative? And we know the y derivative at T0. All we need is to use the governing equation. So our governing equation, remember the y derivative at T0 is so this derivative at T naught is T naught at y naught. So, and we know the first point, which is the T naught, y naught. We do have exact slope, right? If we just simply evaluate the function, the right-hand side function. So we know the slope of the tangent at the first point. So that is this function. So once that is the slope is replaced by this right-hand side function at t0, y0. And then we have this linear approximation to the solution curve. It's just a straight line equation. So certainly it is a very simple function to approximate an unknown curve. But if you use this simple function, suppose you want to calculate at t1, right? At t1, what is the approximate solution, which is called y1. So as soon as you replace t with t1, you will get the y1. So as soon as this is t1, you will get y1. That is this formula, right? t1 minus t0, which is the step size h, one step, f at t0, y0. And this y1 is approximately equal to the solution curve at t1. Yeah, you see this, we just simply try to see that approximation at t1. So this notation is the exact solution curve, y, evaluated at t1. So that can be approximated by this linear function. So this formula is easy to implement because once you get t0, t0, y0 is given, then you can simply get y1, right? So once your y1 is found, and then at the same pattern, you just use y1 and t1, y1, you get y2. And you can always get the next y value using the current t, j, yj. You can get the next approximate y value. So that is our how we implement the Euler's method to find the sequence of y values of the solution curve. And this is a concrete, and this is a concrete problem, initial value problem. So the initial t at that is what we call t0 is 0. The y0 is 1. So that's the initial data. And the right-hand side function, which is the function f, right? This function f, it is dependent on t and y. So it is that function, t minus 2y. So that is our right-hand side function. And that's our function to determine approximate slope. And it is a linear equation, and it's possible to get exact solution if we use our technique, right, for solving a linear equation. And integrating factors method, we can quickly get exact solution. And of course, after you do the integration, you have arbitrary constant, and you impose this initial condition, you can determine a unique solution, which is this given problem. So that's not our emphasis. I just want to say we can possibly get a unique solution for the initial value problem. But today we want to find the numerical way of solving this. Suppose you do not know how to solve it. So how can we numerically find an approximation to the solution of the initial value problem? But I want to add a remark, like if you apply the Euler's method, one thing to be aware is once you get this y1, it's approximate. It's already an approximation to the true solution, which is y at t1. So as we can see from the picture, so y at t1 is smaller, right? It is below the y1. So if at this y1, which is, let's call it, this is a point t1, y1. And it's not really on the exact solution curve. But if we use this to get a slope, so that means if we use the slope function on the right-hand side, so t1, y1, that is the slope that is only to approximate this tangent, right? This is the tangent line slope. Because this, in order to get the real accurate slope at this point, we need to use the exact y value. That will give you the slope, right, at this point, if we know the exact y1, I mean the y value at t1. However, we only use approximate y value, so that means the certainly it is approximation to this slope. It's not really same as the tangent line slope at t1 of the curve. So here we use approximate point, use approximate slope. Yeah, so I will say a little bit different than that slope of the blue, right? So it's approximate slope to the blue. And then we do one step. So that is how we get to the next point, y2. So that means using Euler's method, only in the first step, our slope is accurate. That is the slope at the slope at the first point by evaluating the function, the right-hand side function. But later, because our function values are approximate wise, then the slope is only approximate slope, and also the y value also. So that means that in future steps, the t1, y1, that's a point, only approximate point, not exactly on the curve, and slope at this point, slope at the of the solution curve is also approximate, right? We use this, and then we construct a line using point slope formula. So that's how we proceed. But the formula is just the same. So so when you calculate using a step size 0.2, and then we can see the step 1, you will get, that is, you start from 0 for that problem. And if your step size is 0.2, you get, that's our T0, that's T1. And next step, you will get the solution, approximate solution at 0.4. So that's another, and T3 will be 0.6. So you increase by 0.2. So T3, etc. So you can keep going. So here is the table in 3 steps. So in step 1, but the initial point is given when T naught is 0, Y naught is 1. So we do have the first point, right? So we can draw the first point, 0, 1. And so in order to get the next, so this is Y value, Y naught at T naught. So then how do I get Y1? So Y1 is Y naught plus H, which is 0.2. And the right-hand side, F, it's T minus 2Y, right, for the equation. And Y0, we know Y0 is 1, so we can put a 1 here and 0.2. And now to calculate Y1, we use T naught, Y naught, right, for this function. So this is our function of Ty at this node. Okay, so T naught is 0. Y naught is 1, so minus 2 times 1, which is still 2. So then you see this part is the evaluation of the right-hand side function. So we get, when T0, Y0 values are substituted into this function, we get 0 minus 2 times 1. Yeah, so that's what we have. So which is -2. So this part is done. After we have it, then we multiply it by the step size, H. So multiply it by step size. After we multiply it by step size, then we add Y0. So this is a Y0. After we do this much, then we are done. We get all this together, right, will be Y1, which is 0.6. Okay, so once you get Y1, you can continue to get Y2. So from the table, you see we get 0.6 for Y1. And then how do I get Y2? So Y2, just continue to use the same algorithm, Y1, H, the function value at T1, Y1. So it is, what is Y1? Y1, we just found it, right, to be 0.6. What is the H? Still 0.2. That's the same. It's a constant step size, 0.2. What is the right-hand side function? Function is given in the equation. So that equation is T minus 2y. Remember, our equation is this equation. Yeah, with the initial data, right? So this equation is its right-hand side is T minus 2y. So we're going to use that again, but this time to calculate y2, we need to use T1, y1. So we found it already because T1 is what? 0.2. That is our T1, right? When J is 1, that's our T1. What is Y1? Y1 is 0.6. We found it already. So we are going to use 0.2 minus 2 times 0.6. So that is our right-hand side function. That is the first, you need to evaluate the right-hand side function. And then next, what do? We need to multiply it by 0.2. And then add the y1, 0.6 to this. So that is to get y2. So you see, we continue after you get the right-hand side function, you will multiply it by 0.2 and then add the product. Yeah, add 0.6 to the product. So here, then finally we get a value, which is y2. And that is 0.4. So 0.4 is y2 value. So this is how we proceed. So you see this table. In order to get y3, what do? You first calculate the right-hand side function at the previous node, right? That is, in order to get y3, then you need to use, this is actually y at t3. So the t3, so in order to get y3, you need to evaluate the right-hand side function, which is f at t2, y2. So you must know what is your T2. T2 and Y2 found already, right, in the previous step. So T2, Y2. So these two values will be used here to evaluate the slope function. So once your T2 minus, T minus 2Y, you see, 2 times the Y, Y2. Okay, once you get that, that's the evaluation of the slope function. After that, you will multiply this, the value of the slope function by the step size, by 0.2, and then add the y2. So this y2 will be added. And then this is the result for y3. So after 3 steps, you already see the calculation method. So you can apply it. And so in case you want to know how good our Euler's method is doing, the first point is same as the exact value. And the second point differs from the exact value of the solution, because we know the we can possibly find the exact solution for that initial value problem. So we just simply use that exact solution curve, and we can evaluate that curve at T1, T2. Then we can compare the approximate solution with the exact solution. Then we can see the error. So this is this column shows the approximate solutions, and this next column shows the exact solution. So this is exact solution at you see. So basically, that's the exact solution at 0, and then exact solution at 0.2, exact solution at 0.4, exact solution at 0.6, etc. So then we can do the difference. You see, so this at T0, of course, no difference. And at T1, which is at this T, and there's a difference. You see the approximate solution is less than the true solution. So the error is negative when you do the subtraction. And then the approximate solution compared to the exact solution, yeah, you get even more negative number. So then you see the error at T3, which is this T. So yes, from T2, this is a T3, now 0.6 at this T, the approximate solution compared to the exact solution, that's the error. So you see the error at different T values. Now we are going to see the exact solution curve, which is yeah, so this solution curve will be plotted with approximate values. So we can see how good the approximation is. So from on this picture, you see the step size when it's 0.2. So you go forward. Which one is the approximate solution when using step size 0.2? And this is the one, right? Starting from this initial point, and then we move forward at 0.2, we get this value. At 0.4, we get the next value. At 0.6, we get next value, and etc. So you can get a number of y values, and you compare it with the exact solution, which is the solid line. See, the solid line represents the exact solution. Then you see at each t, right, this the difference. So we can see that's not the best approximation, but it seems we got improvement when we make the edge smaller. So let's look at another step size when the step size is half as before. So previously we used the 0.2 and now we use 0.1. And that means you need to calculate the approximate y. So at 0.1, 0.2, 0.3, 0.4. So you will get more approximate y values. So here is, we will get at 0.1, at t is 0.2, when t is 0.3. So that's actually another curve. So you can see this one. Yeah, so you see this, and at 0.5, at 0.6, at 0.7, 0.8, 0.9. Yeah, so that curve shows a better approximation compared to the previous when we choose 0.2 and now we choose 0.1. So we get a better approximation. And then if we make the step size even smaller than this, 0.1, then we can choose 0.05, right? Half of 0.1. Then we can see a further improvement for this problem. So but you certainly will need to do more steps. That means more calculations to get more y values. So this is another one. So if you go still from here and then you move, and how many more steps? So let's assume from 0 to 1, suppose for this interval, if you use 0.2 each step, then you will calculate you will do 5 steps. 1, 2, 3, 4. Yeah, so you go 5 steps. You can get to 1, right? So from 0. And then that means 0.2. Of course, you will need 10 steps from on this interval from 0 to 2. The entire interval, you need to do 10 steps. But if you make a smaller step size, when the h is 0.1, then how many steps you need to do? You would do 20 steps. So that means for this step size, we need 20 steps. And then for even smaller, like when h is 0.05, then you will need 40 steps. So that is to get a better approximation to the exact to the solution. We can do more work using smaller step size and get a better approximate solution.